Tangent. This is different than SOHCAHTOA tangent. All right, different than this is tangent in a circle. A tangent. What is it? First, what is a tangent? It's a line, right? It's a line, not a line segment, a line that intersects the circle in exactly one spot. That's it. Okay, so it touches the circle in exactly one spot. So you guys see here in my first diagram, I have 3 different tangents drawn because let's see, this one only intersects it at point F. This one intersects it at point C. This one intersects it at point B. So a tangent in a circle, a tangent line, only intersects the circle one spot only. Everyone look at my second diagram. I want to go through each of those and somebody help me tell me why those wouldn't be tangents. Why isn't RS a tangent? Why wouldn't I say RS is a tangent on my second diagram? Doesn't even touch anywhere. It's got to touch once and only once. Doesn't even touch anywhere. Why not PQ? Touches twice. All right. What's wrong with TU? Well, it touches once, right? At U? Tangents are a line, okay? Not a line segment. And plus, what is TU anyway? That's a what? A ray. How long have you been in this unit? What is TU? A radius. That's a radius, yes. And why doesn't VW work? Touches it once. It's not a line. Not a line. It's got to be a line that touches it once, okay? Everyone good with the tangent? And by the way, there are infinite tangents you could draw on a single circle. All right, going all different angles, but it's got to intersect at one spot only. All right, speaking of that spot that it intersects, I'll tell you, these mathematicians way back in the day were pretty clever. Where it intersects the circle, that's called the point of tangency. How about that, huh? You like to have it? Great. No, point. We made it easy just for you, probably. They thought they knew you were going to have me one year, and there it is. Point of tangency. That is where the tangent intersects your circle, the point of tangency. So here's what I want you guys to do for me. There's a theorem box right there. Off to the right-hand side, can you fit a nice little circle for me? I want you to see this theorem, just not read it. Put your center in there for me. Wherever you think your center is, just put your point there. Go ahead, draw a tangent line. I don't care where it is, draw your own tangent line. A line that intersects the circle in one spot. And mark the point of tangency, where your line intersects your circle. All right, here's your first theorem today, but we've had a lot of them so far this unit. Draw a radius to the point of tangency now, please. If this happens, if you have a radius drawn to the point of tangency, those two are perpendicular, which means what? They form a right angle. Okay, so everyone take a look at your diagram. If you have a radius drawn to the point of tangency, it's perpendicular. Okay? But it's got to be drawn to, it can't just be any radius. It's got to be drawn to the point of tangency. All good? All right, ready to try it out now? Take a look at that triangle here. And we say, hey, assume that if it looks tangent, it is tangent. And I'm looking for angle X right now. Angle X. Have your calculators out. Yep, have them out if they're not out right now. All right, ready? That's fit. How do I get angle X? Well, now this is why we got to know our facts, because you're going to stare at this and be like, I have no idea if I don't know my facts. Tangent, radius, what happens where they meet? 4, what happens where they meet? 90-degree angle. So because you know your circle facts, this becomes a very easy problem now. How can you find X? 13? There you go. But again, hey, you don't know that's 90 unless we know our facts. Trying to stress that point. Charlie, what does that end up being? 32? Great. Thank you. All good? All right, how about 2? Find the value of x. Again, I can't even start anywhere unless I know my facts here. Take a look. You got a tangent. Everyone see radius CB? That's a radius, right? So anybody, what's going to happen at angle CBA? 13 again. Charlie, what's happening at CBA? You get a right angle here. Now we're talking about sides, not angles now. Sides, not angles. It's a right triangle. You know something about all the sides. What have we been using all year long? If I have a right triangle with sides, I know. 6. Pythagorean theorem. Here it is. A squared plus b squared equals c squared. Yeah. All right. What should go in for a and b here? We've been doing this a while. Whoa. Suspense is killing us. It's starting to kill me now because I want to move on with class. All right. Maybe we'll get back to it. The good old school internet, right? Killing me today. All right, I can't wait any longer. So we're x squared, right? Here's one leg, CB. The other leg, 8 squared. And now C is the hypotenuse. How do you write the hypotenuse here? CA. How do I write? Not 2x. What's it going to be? Not 2x. Do I have any coming back at me now? Still rocking. Lucky you guys. Any help?
2 plus x.
2 plus, or I'm going to write x plus 2. Yeah, x plus 2 all squared. Yep. All right, I'll help you out. Here we go. X squared plus 64. Oh boy, don't do this to me. Your algebra teachers last year and next year, your algebra teacher next year is already embarrassed. Not x squared plus 4. What do I need to do off to the side here? X plus 2 times itself, right? Oh, x squared plus 4. And you double distribute, right? X times 2, 2 times x, 2 times 2. X squared plus 4x plus 4 when you combine your like terms in the middle. All right, now we got to move things over because it looks like maybe because I have the squareds here, might have to factor, maybe. Good news for you, though. How do I move the x squared over here? Just stop it. Quit. There's no quitting in here. No, it's always working. God, sometimes it's school internet. All right, I got to move it over by subtracting. I hate doing this. And what happens when I do that? When I move it over? It's gone, right? Everyone agrees it's gone. So good news for you guys. You don't have to factor here because the x squareds cancel each other out. So I'm just left with 64 equals 4x plus 4. And you guys can go ahead now and solve for x pretty easily. So a little heavy algebra there, sure. Connected. $15. We're getting 15 out for x. taking a lot longer than I need to. All good? All right, let's get moving here. Forget the numbers. Keep checking back. All right, number 3, finding x again. Everyone see where the right angle is going to be. Got to know my facts. Radius drawn to point of tangency, point B. Everyone's got it. I'm talking about, watch what happens here. I do have a right triangle. All right, so maybe I can use a squared plus b squared equals c squared. Everyone agree that one of the legs is BA, x. So x squared. The other one, there's just blank. CB, just blank. But you know you should be able to find it. What is CB? Name it. Give me the vocabulary term for CB. It's a radius. And maybe I don't think I've really expressed this enough, though. If you're in the same circle, all the radii are the same length. All right, so what's one radii you already know the length of? What is the length of the radii? 3, so that means they're all 3. All right, so if you're in the same circle, all the radii are the same. So that's how I know BC is going to be 3. And then how about your hypotenuse? Hypotenuse length? 10. 7 plus 3, yep. All right, let's go to town. X squared plus 9 equals a hundo. Move the 9 over. X squared equals 91, I believe. Take the square root of both sides, and I can tell you right now, I don't want that. What are we doing? Put down the calcs. I don't want that decimal, right? There's no rounding directions. I'd probably want this in simplest radical form, but good news, it doesn't break down. So we leave it as the square root of 91. All right. And one more. We should know there's a right angle at B. I definitely know one leg's 12 squared. What about the other leg? CB, anybody? CB? 9 as well. All radii are equal in the same circle. 9 squared. And then just based off a problem we did a couple ago, what about the hypotenuse? X plus 9 squared. Yep. And I hate to break it to you. Sorry, kids. But yeah, it looks like we are going to have to factor on this one. So go ahead and do x plus 9 squared off to the side. What do we have in the middle? 18x and 81. So we end up with 18, because you get 9x plus 9x. Gives you 18x in the middle. We're all good? All right, moving on. 144 and 81, what's that? 5, 2, 225? All right, ready? You see x squared, got to make one side equal to 0. We've been over this a lot this year. I know it's been a while. Got to make one side equal to 0, so move the 225 over. Subtract it over. Somebody a little help there. What do I get there? Negative 144. I should have known that. All right, I don't feel sympathy for you here. You're in an above average math class. I don't feel any sympathy. Here we go. Two numbers that multiply to what? I should have two numbers that multiply to. Ah! That should add to, Spence. Add to. No! Flip it. They multiply to the last term. 144 add to the middle. 18. All right. So yeah, everyone's got to play around in their calculators because I'm not doing this for free. Two numbers that multiply to 144 but add to 18. We find those numbers? What do we have? 24 and 6. Relax, I got it. Relax there, big dog. These kids. Okay, you got to play around with your calculator. Those are the numbers. All right, now let's do the answers. So one answer will be x equals negative 24, the opposite, and x equals positive 6. And let's have an awkward staring contest until somebody tells me what's wrong. The math's correct. Problem with that being negative 24? Can't have that, right? Can't have that. So we got to reject my negative 24 and just keep 6. Yeah, it's getting, woo, wake up there. A little wake up call for that one. And I know people are just sweating seeing this next page because it's approved. For time's sake, because I never like to go the full time teaching, we'll use this as a review proof and come back to it. So I'm just going to give you the theorem right now. Okay, I'm going to give you the theorem right now. So what I want you to do under that theorem box, because you have plenty of room, draw yourself a circle for me. We'll get back to that proof when we start proofs and review with it. And what I want you to do here, you don't need to make a full tangent, but just coming from a point of tangency outside the circle, draw me two tangents that meet at the same point outside the circle. Kind of like that. And let's label them here. Let's go A, P, B. All right, if you have this, pretty easy theorem. If you have two tangents that meet on the outside of the circle at the same point, they're always congruent. Okay, they're always congruent. And here's the theorem. We call them tangent segments. We don't call them tangents because remember what tangents were? A full line. All right, so we call them tangent segments. Tangent segments drawn to the same point are congruent. Sometimes students remember this as the party hat theorem. I kind of drew it off to the side, but if you turn it 90 degrees, everyone see the party hat. You're not allowed to write party hat in your reasons column either. I will destroy you if you do. Okay, but that's what you can remember it as, party hat theorem. I just don't see it. party hat. Here, there we go. Good. And don't they have the little rope underneath there for the keep it under your chin? Yeah. All right. Okay, great talk. All right, here's where we can use that theorem now. All right, here's where you can use the theorem when I draw a circle inside a triangle. So take a look at this first diagram. Everyone see how this is labeled as 4? Does anybody see another tangent segment that's drawn to that same point right next to it? So if this is 4, right here, based on that theorem I just gave you, has to be 4 centimeters. Look, two tangent segments drawn to the same point are congruent. Everyone see where I'm going from here now. Now go to the bottom right. If that's 3, everyone see a tangent segment that's drawn to the same point too? That has to be 3 centimeters. And if that's 5 to the bottom left, we see the other tangent segment drawn to it. That's got to be 5 centimeters. And now we can answer the question, what's the perimeter of each polygon? So what do we got? 8, 7, and 9. Oh boy, 24. No?
7?
4 plus 3?
Oh. I did 4 plus 4 plus 2 plus 2 plus 5 plus 5, so.
And then how about 2? I know 8, 9, and that part's 6. What about the other? Now, hey, are we clear? The other part's not 6. That's not how it works because this tangent segment's drawn to that point. The 6-inch one is drawn to that point. They're not equal unless they're drawn to the same point. All right, but I'm still on the hook for that segment. So how can I get to that segment? I got to work all the way around. Ready? If this one's 6 here. Everyone agree? That's the two tangents drawn to the same point. Whole thing was 9. This whole side was 9, so that's got to be 3. See how I'm working backwards? If that's 3, this tangent segment's 3. That whole thing was 8. Here's 5. Here's 5. And now we can add them up now. So I originally had 9 plus 8, and now I'm going to add 11 to it. 28 centimeters. All right, I'm going to let you do the last 2 on your own. I'll give you a couple hints here. How many degrees are in every quadrilateral? In a 4-sided figure quadrilateral, how many degrees? 360. You might need that here, all right? 360 degrees in every quadrilateral. And then what did we mention today? What do you know about all the radii in a circle? Right? So if that's a radius and that's a radius, they have to be equal. All right, see what you can do. See what you can do here with those 2. Remember your theorems from today, right? You got tangents there. You got a radius drawn to the point of tangency. Remember your theorems. This is why this part of the unit's so tough. toughest section of the unit right here, and I think you guys are starting to come on my side. What'd you learn today? That's a tangent. That's a what?
Maybe.
Where they meet, what happens?
Alright.
Right? And what? Same thing on the other side. How many angles do you know now?
3.
Add a 4 in that quadrilateral, right?
Mhm.
Whoa, we're pretty confident.
Oh, yeah.
Oh boy, I don't know about that. Confident back there, Spence? You got this stuff? Really? Okay. Type of triangle is it? Type of triangle is it? You know, the radii are equal. So what do we know from this year's isosceles? There you go. All right, so for 3, did I stop recording? Nope, didn't even stop. All right, so for 3, we use the theorem I gave you guys today. Radius drawn to a point of tangency, right angle, right angle. 360 minus 90 minus 90 minus 130 gives me x. What do we get there? 180, 50? So there's 50. And then over here, other than knowing the radii are congruent, there's no more circle facts. What type of triangle is in there? What do we call that? What type of triangle? Isosceles. And what do you know? Not only are the sides congruent, but base angles are equal. So if that's 50, this automatically becomes 50 because it's isosceles. And now x will be 180 minus 50 minus 50. X equals 80 degrees. So hopefully we're opening up some eyeballs here that, yeah, this is not the easiest here. Guys, you got to grind for me this weekend on that assignment. All right, I know it's a couple more problems than usual, but we're not going to get any better. And I'm not stopping to slow down.